Hi, this video is part of a series in which I learn about programming a retro video game on the Commodore 64 in assembly. The code I'm using is from the game Supernatural, written by Georg Rottensteiner. You may also know the game as Guns and Ghosts. This is not a tutorial, just me learning game programming. Enjoy the video. Coders, good afternoon. Step 27. In this step, we will be adding a new enemy. Most of the steps of adding a new enemy we've already seen, so I'll run through them quickly. There've been some tiny changes to the code, which I'll mention briefly. The main part of this one will be the behavior of the new bat. We're gonna be looking at a new bat. Let's just have a look at it first, see what it looks like. I'll get a controller. There it is, Supernatural. Blow it up a little bit. Here we go. This is the new bat. As you can see, it starts out just going left and right. There's no odd things. When I hit it, nothing happens in the behavior, but there it goes. It changes its behavior. As you can see, it will disappear and appear randomly. Sorry, my microphone sank. It will disappear and appear randomly, and it will attack me. And I just dropped from the sky there. Minor bug. It can also change direction, and it has a new animation. So that is the behavior that we're looking at. It's not very dynamic, and although I haven't played Supernatural to the end of the game, I in the first few levels that I've played, at least, I haven't seen this enemy exactly, but I'm sure some of the code will have survived. I seem to have some trouble running left and jumping. Right and jumping is okay, but left, and I can't imagine that it's my controller. It's just I can't seem to move left and jump, or like move left while jumping. So that may be a little bug. I have to look at that. Anyway, that's what we're looking at. As always, I'll start with the data section. Let's have a look. Some of the data has been moved. It has no effect on the game whatsoever. The screen data. Let's see if I can find it quickly. 4626. That's close. So this has been moved. Also, the tables for the character of each screen character, first character of each screen line, it's just been moved down. No particular reason. Just I guess it's just cleanup. Then, of course, when we add a new enemy, let's slowly go up here. 4283. Maybe I should start bookmarking these. 4283. There's a bat animation. That's not new. There is a new enemy type, which has health points, 3 health points. These tables are all indexed by type. They start with the name type, so they are all indexed by type, and this is the new type. It doesn't start multicolor. It does start with a foreground color 3, and the type is here. No, wait a minute. Start sprite. Let's see. Oh, this is the first a representation of the sprite. Let's have a look at the spriter. This is what that refers to. So when this bat starts, it starts out as this. Let's see what the code is. It's 41. Yeah, probably. Oh yeah, we'll see what that means. It points to this at least. As you can see, also there are two new shapes. One is an empty shape, and one is this. What do I call this? The poof shape. Anyway, oh, the 40. It refers. See the 40 here. When I hover over this, it says 41. That's funny because the start sprite is 41, and that would refer to this actually. So it would start out like that. Weird. Let's also look at the rest. Let's see, vanish. Oh, of course, we have the. This is the whether or not it's an enemy. Yes, it's an enemy. And this says something about the behavior table when hit, high address, low address when hit, and the regular behavior, bat vanishing, and the lower part of that address, so that we know, the game loop knows what to call when it runs into an enemy of this type. And what else? Well, that's it for the data, at least. Let's see if I can, if there's anything new at the top. Yeah, of course, adding a new enemy. I'm just scrolled all the way to the top of the code. Here are these two new sprite shapes: sprite shape invisible and bat vanish. It does kind of bug me because which did it say bat 1? Which let's see, what did it say? Start shape, or is it start position? No, sprite bat 1. Start sprite bat 1. What is that? Oh, wait a minute. Sprite bat 1. Sprite bat 1. That's that one. Right. Sprite bat 1. That's sprite base plus 1. Okay, sprite base is 40. Okay. Yeah. So just going back to the sprite overview, sprite 1, that's that one. That one. So not that one, but that one. It's throwing me off because of the 41, but this is decimal 41. Idiot. Okay. We have to look at the code. Type bat vanish. We have to give it a type number. There it is, number 7. And that's basically adding the enemy on the data side. Now we have to. We made a little level that demonstrates the use of the new enemy. So we start our game at level 2 this time, level 3 actually, counting from 0. And the next step is making the thing move. 2841. There we go. 2841. Now this is where it all gets interesting. Just as a little side note, we use these same tables all the time, and over time you may start to forget what they do. So I've added to the project a little document which I call documentation. If I can grab it here. There it is, supernatural documentation. This is for step 27, and it's basically just a data description. So each and every element of data, so everything at the bottom of the code is described here. It's also helpful for me to, if I need to look up things, but this will tell you for every table how it's indexed and what kind of value it will yield. So sprite state I'll see if I can sprite state. There it is. This is indexed by sprite number, but we can tell that from the fact that the table is named sprite underscore. So this will tell you the way it's indexed. Sprite number, it records the current state of a sprite. The thing is that state can be used for anything to influence a sprite's behavior or whatever. In certain states, some sprites will be undetected by collision detection. We've seen that, and we will see that here as well. Basically, this sprite state can be used for many different things. It's different from the sprite move position, where this actually has to behave a certain way for the code to make sense of it, and this changes with every sprite. We'll see how we use it in this case. Sprite state. There we go. Remember that this code is called on every frame. When the game loop detects that this type of enemy is present, it will call the behavior for this sprite. So this happens every frame. Now, we check the sprite state. If it is anything other than 0, it will go to the not normal code, which starts here. Otherwise, it'll do a normal update, right? So we'll look at that. I'll go to the declaration of normal update. And there it is. We use a delayed generic counter. That's to make sure that we don't do things every frame, just every other 3 frames. There's either a no animation update or an animation update. So we animate it every frame, I suppose. No animation update. No, we update it every frame, but we don't animate it every frame. So what we do here, if the sprite is to be animated, we increase the animation position, we load it. We AND it with 3, so we only get the first 3 bits of that. We transfer it to Y, and then we take the next animation and set the next shape. I wonder how that toggles it between the 40 and the 41, because basically we just, oh, wait a minute, it doesn't do that. Let's see, let's get the sprite shapes back, because this meld that I use is a modal window, and it won't, it'll hide other windows. So this is basically what it's doing. It's going, this is like the normal behavior. It's going through these, increase sprite animation position. I haven't seen which sprite animation position it starts in, but we just increase it, do we? I have to look at that. A bit of online research here. This is the level data, so that's all at the bottom. I've just gone back down to the data section. Yeah, this is very interesting. Let's see. Bat animation. Right. This is what it reads, I'm sure. Bat animation. But where do we know that? Sprite, start sprite, bat 1. Bat animation. Let's see if that's used anywhere. Yeah, but we're not doing that behavior. Yeah, this is the... How do I know what that is? Oh, it just says right there. Jesus. Okay. It starts at 0 because that's where it's initialized. We increase it, we load it, we just take the last the three least significant bits, store it back, and then get the next animation from bat animation. That's what it said right there. So that determines the way that it looks. Right. So every few frames it does that. Otherwise, we check the sprite state. If it's not equal to 0, then there's no action. Nothing happens. If it is equal to 0, that is now. We load the sprite direction. If that is 0, then we do the move right code, which is move the object right. Blocking, this moves it right if it's not blocked, so we prevent it from flying off the screen. If that comes back 0, then we have to toggle direction. The same is for the left move. So this code makes it move left and right as we saw. Toggle direction is easy. Sprite direction is either 0 or 1. 0 being right, 1 being left. And we exclusive OR it with 1, which means just flip the bit around and store it back. So it goes from 0 to 1 and from 1 to 0, and then it jumps out. So that's normal, nothing's going on situation. And it'll keep doing that unless something happens. So what happens? It's the hit behavior. So we're going to have to look at the hit behavior, which I'm hoping is right. Hit behavior vanish. This is our thing. It loads the current sprite state. If it's not equal to 0, then there's no hit, nothing happens. If it is 0, we load the sprite vanish shape, update it. When this happens, the sprite shape is immediately updated, right? The VIC does that. This is a VIC register, and it's immediately changed. And we change the state to 128. This is just our own chosen state. Now I scroll back up because on the what's going on now? On the next iteration, on the next frame, this behavior code will be called again. And this time it'll load the state and it'll say, well, it's not 0. So we go to the not normal code. Now, here it happens. We compare it to 128, which it's been set to because that's the behavior when it's hit. It goes to vanish 1. We do the delayed counter thing, and it decides either no special behavior. No special behavior is, I think, where is no special behavior? Oh, I skipped it. Shit. Going back up. Oh, no special behavior right here. Oh, okay. No special behavior is just an RTS. Nothing happens. That's funny. So we just skip a few frames. And otherwise, we make the sprite. So we've just been hit. We make the sprite invisible. Remember, this makes it this sprite invisible is the empty shape. We make it invisible immediately. We increase the sprite state, so now 128. We generate a random number. We add 24 decimal. So these are pixels, and we store the sprite move position. We store that value in the sprite move position for this sprite. Now, this means normally this says something about a pre-described movement of the sprite, but this sprite doesn't have that. It doesn't, like when we did a jump, the sprite move position is just an index into a table that says how many pixels we go up each frame, right? And for falling, it's the same thing. And for the figure 8 bat, we also describe some movements. Now this is just excuse me, this is just another value. We put a random number above 24 into the sprite move position, and then we jump out. Now the state is now 129, so that's the next, and we're hidden, right? So 129, next frame, we do this behavior again. We are 129. We go to hidden. What do we do when we hit? We start decreasing that random value again. See, it doesn't really have a meaning. It's just, this is just a time value. So we're waiting for a random number of frames until we unhide. Otherwise, we just jump out. So we're hidden for a while. And then when that period is over, we unhide. And we start looking for a position. So we take the player's character position. This is the sprite character position. It's indexed by sprite, but we don't index it. So we get the first value, which is the player's character X position. Now we... when we're smaller than character 10, so we're in a position that is smaller than character 10, we spawn on the right side. Otherwise, if we're below character 30, we spawn on the left side. So that's when we're towards the left side of the screen, we want to spawn to the right side of the player. When we're on the right side of the screen, we want to spawn on the left side of the player. And otherwise, we just randomly choose. So either... we generate a random number, we AND it with 1, and if it's 0, we spawn on right, otherwise we spawn on left. Okay. I remember this technique, a compare basically does a subtract, and we look at the behavior of the carry to determine whether the carry was set or cleared, to see which value was larger. Spawn on the left, so we load the character's X position. We set the carry because we're going to subtract. And we subtract 5, and we store that in parameter 1. Overriding whatever was there, but that's like a global variable. We load 0 into A. We store that in sprite direction for our sprite. So we're spawning on the left side. Sprite direction 0 is right, so we're moving right. And then we find a Y spawn position. So that's the next step. We first do an X position, then a Y position. If we'd chosen to spawn on the right, we would have done something different. We load the character's X position. We clear the carry because we're adding 5 again. So we're adding 5. We're starting 5 character positions away from the player, either left or right. This time we load 1, which is left. We spawn on the right, so we have to be moving left towards the player. We put that in our sprite direction, and then we find the Y position. Basically, it's the same. We either spawn below or above. Well, it's exactly the same code. We clear 5. This time we use the sprite falling. Sprite direction only says something about left or right. We could have used this for 4 directions, but we don't. We've made this into a Boolean. Same here. Sprite falling is also a Boolean. Yes or no. 0, no. 1, yes. And then we go to reposition. So we calculate the sprite position from character position. Now, if we look at this function, parameter 1 wants the character X position. Parameter 2 wants the character Y position. As you can see, that's there. and X is a sprite index, and it calculates the real sprite coordinates from screen position and sets them directly. So, and then we increase the sprite state. We were 129, and now we're 130. We set the bat vanish shape, and we paint that. So are we still vanished? Let's see. We go back on the next frame. It's now 30. We go into spawn. So we spawn. Again, the delay generic counter, so we don't do it immediately because otherwise it would just all go too fast. First, we start by setting the sprite state to 1. We set the sprite shape to bat 1, so we appear again. And then we do an attack flight because we're now state 1. We end up here. If it's not that, then we go to no special behavior, but it is 1, so we go to attack flight. Now, what does attack flight do? Still in the same function. We increase the sprite move position. Look. Okay. So we try to. This is funny, right? This is funny. And I like this in game program. This is where the game actually happens, right? It would be easy to program something that would just kill the player, but we're giving this enemy a sort of basic intelligence. We're going to try in 80 moves to get the attack done. We're just going to move in the direction of the player. And there's nothing added. That's the try. And we hope to hit the player. And there's no hit detection in this routine. This just updates the enemy position. There is, of course, in the same game loop, a collision detection routine, which tries to detect whether the enemy has hit the player, yes or no. But we don't do that here. We just blindly go towards the player. And we try to do it in 80 moves. So attack done is, let's see, because that's the end of the attack. Sprite state goes back to 0, and we jump back to hit behavior vanish. So to the standard state. That's the attack done. We're no longer attacking. If we're 40 frames on, we can change the fly direction. Let's leave that for later. Let's see what we do. If we just start the attack, we have our direction. We either fly right or we fly left. Right? So you can see here, fly right is just object move right and then fly up down. Otherwise, we do fly left. We store our sprite number in parameter 5 here. Object move left. You see, this is a danger in the programming. If I just called this function now, object move left, I don't have a way of knowing whether or not it's going to overwrite any of the parameters. It might, because they're global parameters. I'd have to go into the function and check whether it does. And my guess is that it does, because otherwise we wouldn't be using parameter 5 here. You know, that's a little... that's assembly language for you, of course. It's just there's just no local variables or anything like that. That's all higher programming language stuff. So we have to solve it this way. But we have to put something in the documentation about which values it destroys. Anyway, that's what we do, and we restore it here. See that? So X is destroyed as well. So anyway, back on track. The object either moves left or it moves right, depending on our current direction. Now we set it in a place and decided the initial direction there. then we're either falling, so we do a fly up, or we are not, and we do a move down, so move up, move down, and we change. Oh, okay, and then that's it. So we either fly up or fly down. I haven't, though, because it goes in a diagonal, doesn't it? Oh, wait a minute. It does a right and a down. Okay, yeah. So it does a right and a down, or a left and a down. So that's the diagonal. So after 40 moves, we change fly direction. What does that do? Change the direction to avoid flying out of the screen. Okay, but I've seen it go down and then up. Oh, okay, so it just reverses direction. That's what it does. So we load the sprite character. We load our own Y position. We compare it to 5. Oh, okay. So if Y is 5, so that we're near the top, we do change Y. We go from falling to not falling. If we're 18, which is, remember that we don't use all of the screen. We have a number of lines of text, and then we have the border. So 18 is a value near the bottom of the screen, and compared to 18, check X direction, change Y if we're going out, compare 18. Oh, otherwise we also change Y, of course. Checks X direction, it's the same, 5 on the left side, 32 on the right side, change X. Again, sprite direction, it's either 0 or 1, and we just flip the direction. It's easy as that. And then we're done. And that's the attack done. So that is the, and we've already seen the hit behavior. So what we need to take from this is describing the behavior. Well, this is, we can see that it's still quite static. the enemy just goes in a, at a constant speed. It doesn't like swoop down or changes speed. We may have to add that later. But the basics are there. We just describe the attack. We don't do anything illegal. Basically, we just give it a basic intelligence. We look at where the player is. That's what we do, and then we try to move there at our own speed. Up, and then we avoid flying off the screen. And that's it. And that's everything, because there are no other changes. That's the whole thing. So I hope you enjoyed that. And we're on to the next step. So that'll be 28. Thanks for watching, and I'll see you next time. Bye-bye.